Alright, so we start from the point where we stopped earlier. We discussed why do we need modulation. So, we need modulation so that we can use the channel very effectively. We need modulation because there is a constraint on the physical layer that you cannot make very big antennas. You need to shift the frequency of operation to higher frequencies, and higher frequencies, the power required for radiation also there is an implication, but let us not get into those the physical layer implications. Now, what you need to note here is the difference between bandwidth, carrier frequency. We will keep using the words bandwidth and carrier frequency. Carrier frequency indicates the frequency of your carrier signal, whereas the bandwidth is decided by the message that you want to transmit. Calculated voice bandwidth was certain, 4 kilohertz in case of analog, but the moment you made it digital, depending on the quantization you are doing, depending on the vertical resolution that you are using, the bandwidth required could be different. Okay. Now, we move on to analog versus digital. Now that we know that we need modulation, we now see what is analog modulation, what is digital modulation. Not going to go into the details, but to just give an idea, this is a picture that shows the voltage. So, this is your message signal, that is your modulating signal. Simplicity, a sinusoid is taken because it is an analog signal. Classic example of an analog signal is a sinusoid. And here you see a digital signal which is a 1 or a 0 which you want to transmit, which you want to modulate and transmit. Now, in case of analog modulation, you see you have a certain carrier frequency. This is the FC that we were talking about. You are either modifying the amplitude or you are modifying the frequency. So, you have high frequencies and low frequencies, or you are modifying the phase, which looks similar to frequency because phase and frequency are very closely related to each other. Differential instantaneous derivative of phase is your frequency. So, that is why these modulations look identical. So, this is your conventional traditional analog modulation. As we said earlier, older telephone signals used to work with analog modulation. Whereas in the digital modulation, you see that whenever it is 1 or a 0, 1 represents a high, a 0 represents a low, and again a 1 represents a high, a 0 represents a low, and so on. This is what is called as ASK, and ASK stands for amplitude shift keying. You say keying here in digital modulation. This is also called as OOK. OOK is on off keying. We will interchangeably use ASK or OOK to represent digital amplitude modulation. In terms of FSK, you will have a 1 or a 0. So, there are only two frequencies between which your carrier frequency is switched between only two frequencies, because it is a digital signal. So, you can have only two states. So, you have a high frequency and a low frequency, unlike analog FM signal where the carrier frequency continuously changes. Okay. Similarly, in PSK you have 1 and 0, and you see the phase jumps corresponding to 1 and 0. So, we will talk about digital modulation in detail, which is relevant to optical communication a little later, but this is just an introduction to the analog and the digital modulation. Now, if you use a carrier frequency FC, what would its Fourier transform look like? If I just have a sinusoid, delta function, it will be a delta function. The frequency spectrum is a delta function, is 0 frequency DC plus FC minus FC for only carrier. But the moment you modulate, depending on your modulation bandwidth, it broadens the spectrum. So, one form of it we already saw. We saw that the carrier frequency would have been a delta function, and depending on the bandwidth of your modulation, the bandwidth of the signal after modulation is larger. This is important to understand this, the broadening of the spectrum depending on your bandwidth, because later on when we do optical communication, there are certain impairments that happens because there are certain impairments that happens which is dependent on the bandwidth of your signal, right. So, when you do that, we will recall this idea once again. For instance, chromatic dispersion, it is dependent on the bandwidth, it is dependent on the line width. You may get confused, should I use the line width of the carrier? In case of optical communication, the carrier is laser. Laser will have a certain line width. Should I use that, or should I use the bandwidth of my entire signal? And the answer is, I have already given you, it should use the bandwidth of your entire signal, right. So, that is why I am saying that applying modulation, that this idea you will need it later. You will have it is no more just the carrier frequency, it is no more the line width or the frequency width of the carrier, it is the width of your entire signal, which is decided by the bandwidth of your original modulating signal. Okay. Now, conventionally optical communication is predominantly digital modulation. I would say optical communication, I can go to the extent of saying optical communication is only digital modulation, but there are very few rare exceptions. We will talk about those exceptions later during the course. But for the majority of 99% of the course content, we are talking about digital modulation in optical communication. But recently we are seeing that maybe analog modulation would be better for certain applications. So, when we talk about networks, we talk about use cases, specific use cases, we can go back to this question, should I do an analog modulation or should I just stick with digital modulation, but that is for later, but predominantly it is going to be digital modulation. Okay. Now, why should I do digital modulation? This is again coming from the fundamental communication theory. Digital modulation, it is easy to store because it is 1 and 0, so you can have registers and buffers and memory, you can store that, whereas to store an analog modulated signal is quite challenging. You can multiplex easily if it is digital, your signaling is easy because you are only having to worry about finding out certain discrete states, right. If it is an amplitude level, you are worried about 1 and a 0, right. So, whereas in analog, there are multiple levels of the signal that needs to be conveyed. So, signaling is easier, it is robust to distortion because even if for example, you transmitted something like 1 and a 0 here, the channel did something to the your signal, it became, let us say this, it became something like this 1, let us say became like this, it got distorted. I can still find out a sampling instant and I can put a threshold and decide above the threshold is 1, below the threshold is 0. So, even though a signal is distorted to a certain extent, you can still do recovery. Threshold detection becomes easier if it is digital modulation, whereas I cannot make such decisions in case of analog modulation. I want to get my signal as it is in my analog modulation. Alright, so even if there is distortion, you could tolerate a certain level of distortion if it is a digital modulation. That is not possible in an analog modulation. One of the key benefits is this possibility of signal processing, which means that you can collect your signal and you can process your 1s and 0s, you can find samples corresponding to times and you can process these samples to do certain operations which we will discuss later, like filtering, averaging, low pass filtering, high pass filtering in the digital domain to do some data recovery, which is not possible in an analog signal. You can have analog processing, but you would need to design complicated electronics to be able to do analog processing. Whereas, if your signal is digitized, once you get the samples, you can put it through the traditional digital signal processors to do operations on this received signal so that your recovery is better. So, that makes the possibility of digital signal processing is probably the biggest advantage of using a digital signal. You can also do error correction codes. We will talk about this later in the course, what are these error correction codes and how are they useful. Essentially, you build in redundancy in your transmitted bit sequence so that even if you lose some bits, with the received bits, you can still work out what could have been the original bit sequence. So, instead of sending 100 bits, you would maybe send 110 bits or 120 bits and use some kind of redundancy. There are different schemes of doing that, and you do as digital signal processing, use that redundancy and recover your original bits. All that is not possible in case of an analog processing. But the disadvantage is you need increased bandwidth. You had only a bandwidth of FB, but now you increase the data rate to 2 times FB times the number of quantization. So, you want to transmit all that, you need a larger bandwidth and increased processing, because you are saying, I mean, now you are saying that if you were to do digital signal processing, there is some processing overhead, there is some latency, right? You need to wait, you need to collect, buffer the information, you need to process it, and then you are extracting the demodulated data. That may require some time. So, you need to have faster and faster processes. So, the benefits as of now outweighs the disadvantages. So, we are still using analog digital signal processing. You would use analog processing only when now, see, there are very small chance of using analog processing. I told you that happens when you are trying to process very large bandwidth of information. That is when you try to bring your signal back to analog domain. We will talk about it at a later stage. Okay. So, that is about basics of digital communication. Now, we talk about what are the carrier frequencies used in digital communication. So, we started analog digital signal quantization, we talked about modulation, and then we talked about analog and digital modulation. Now, what is the carrier frequency that one should use, right? Again, do not blindly choose optical frequencies. Depending, so what are the factors to be considered when you are saying, okay, I want to communicate, my objective is to communicate from point A to point B. What should I consider? What are the factors that I should consider to decide my carrier frequency? Depending on the carrier frequency you are choosing, you need to have an appropriate source, you need to have an appropriate detector. So, the first factor to be considered is what is the bandwidth that you need to transmit. So, if you remember, we said that when you have an Fc as your carrier frequency, after modulation, this is Fc plus, if my base band is represented as B by 2 and minus B by 2, the baseband spectrum is, this is S of f, power spectral density. If it has a total bandwidth of B, this is Fc plus B by 2, Fc minus B by 2. Okay. So, if you want to have larger and larger bandwidth, if you want to transport larger and larger bandwidth, what should you do? What should be your Fc? How do you modify your Fc? For a given Fc, if you keep on increasing the bandwidth, what happens at a specific bandwidth? It will cross 0 and it will start folding. You do not want that to happen. So, a given Fc, there is only a given bandwidth that you can transport. People use 0.1 times Fc as a thumb rule to decide what is the bandwidth for a given Fc. For instance, if you are using a 1 gigahertz carrier frequency, the bandwidth typically, I mean, engineering numbers could be different, but I can say that even you can choose something like even up to 100 megahertz of bandwidth. Of course, that number will change based on the kind of modulation you are doing, but as a thumb rule, you cannot go very close to your Fc, right. So, if you want to transport larger bandwidths, we talked about internet bandwidths, you talked about the required data rates, what happens in a minute, there is so much of videos being downstreamed and so on, downloaded and so on. So, you want to cater to large bandwidth, obviously you should increase your carrier frequency. So, as a designer, if you have the freedom to choose your carrier frequency, first question you may want to ask is, what is the bandwidth? If the bandwidth is going to be, let us say 1 megahertz, do I really need to do optical communication? Do I really need to do terahertz carrier frequency? May not be necessary, that is one consideration, right. So, the first consideration is what is the bandwidth to be transported. Suppose I want to transport terabit per second, terabits of bandwidth. obviously my radio frequency 2.5 gigahertz carrier frequency is not sufficient, right. So, that is one consideration. Second is attenuation. How is the channel behaving to your carrier frequency? Is the channel transporting the carrier frequency without attenuation, or is it attenuating my carrier frequency? For example, we'll talk about attenuation in detail. So, I will give you the example then, right. Atmosphere, for instance, has different attenuation for different carrier frequencies. So, if you want to do your channel is your free space, the channel that you want to use is it's a free space communication link. You would obviously go and check what is the attenuation spectrum, attenuation as a function of frequency, and pick the frequency which has the lowest attenuation, so that you do not have to spend a lot of power in transporting the information. Third is, do you want to do point to point link? Do you want to do multicasting? Are you kind of relaying to so many people? Or do you want to do, let us say I want to connect from my laboratory which is in the 3rd floor to my office which is probably in the 5th floor. Is it just point to point link that I want to do? Or is it like a radio? I want to kind of multicast. Depending on that, you will choose your channel, you will choose your carrier frequency. Then most important thing, what is the cost and what is the ease of deployment? You cannot have a fancy solution where deployment is really hard. You come up with some frequencies which are really exotic frequency where the loss is really low, but I can't find the transmitter, I can't find the receiver for that. That is not also going to work. The ease of deployment, it could be a hilly terrain. Laying an optical fiber could be a very difficult task, but I may have 2 hills. I could put a microwave transmitter on one side, I could put a microwave receiver on one side. Let us say there is a river in between. It is probably easy to just put 2 microwave antennas and do a point to point communication rather than trying to lay an optical fiber through a hilly terrain, right. So, depending on the situation, you will again decide what should be my channel, okay, and depending on the channel, you will decide what is the carrier frequency. Then security. Is my information secure, right? These days security is becoming also a very big concern, because through our internet we are also using all our unique identification numbers and things like that. So, can I tap my information? If I use a coaxial line, you know that the electromagnetic, as you go to higher frequencies, the coaxial cable will start radiating the information, which means I can keep an antenna nearby and pick up whatever is being transported. Is that okay in your link? Some cases it may be okay. For example, FM radio, I mean its security is not an issue, anybody can get that information. But that may not be the case for maybe a link that is connecting one bank to the other, right. So, depending on the situation, security is also becoming a concern. Now, on the left side, what you see is from ITUT, the possible carrier frequencies are anywhere from 10 power 15 hertz. 10 power 15 hertz in terms of terahertz is, what is 1 terahertz? 1 gigahertz is 10 power 9 hertz, 1 terahertz is 10 power 12 hertz. So, this is 1000 terahertz to all the way down to 1 kilohertz. These are the possible allowed carrier frequencies. This is not the bandwidth, we are talking about carrier frequencies, right. These are the allowed carrier frequencies where one can use communication links with, and which it is not just one can use, one is using for different applications, which will range from telegraph to submarine cable, it is of the order of hundreds of kilohertz, to radio, shortwave radio, VHF, UHF and so on. This is shortwave radio, and this is microwave link, microwave radio, where you are at gigahertz frequencies, and then you have a jump here, and then you have optical communication. So, the carrier frequency for optical communication is of the order of hundreds of terahertz. Exercise for you. What is the wavelength for visible light? Visible is 400 to 800, 300 to 600, so on. Let's pick a wavelength 532 nanometer. Can you recognize what wavelength, what color is this? It's green. Exercise, what is your carrier frequency for this? So you know that C is f lambda, we are talking about free space propagation. So f is C over lambda, 3 into 10 power 8. Let's take 500 nanometer, so that it's easy for us to calculate. 500, 10 power minus 9, 1 nanometer is 0.6 into 10 power 15 is 600 terahertz. So if you are using green for communication, your carrier frequency is 600 terahertz. Green, by the way, is one of the favorite wavelengths for communication for a specific use case. What is it? Underwater communication. Submarine wants to communicate with the buoy, or between submarines there is a communication link. Green or blue green is a favorite color because channel attenuation is minimum for that color, for that frequencies. So if you are using submarine free space optical communication, you would choose 600 terahertz as your carrier frequency. But in an optical fiber, green has a very large attenuation. So we will talk about attenuation in optical fiber separately, but green is a color, or a blue green is a color for which is used for free space communication in underwater communication scenarios. So that's the left side, wavelength on this side and carrier frequency on the other side. You see, this will go into nanometers, 600, 500 nanometers, whereas if you are talking about microwave, that is in centimeter. So there is this class called as millimeter waves, which are becoming very popular these days because the 5G standards in wireless communication is also talking about using millimeter waves as the carrier frequencies. Currently your cell phones are using something like 2.5 gigahertz or 2.8 gigahertz as your carrier frequency, but the next generation communication, wireless communication system is talking about using higher carrier frequencies, and one such carrier frequency is 26 gigahertz or 28 gigahertz depending on which country you are, right, and that comes under the class of millimeter waves, right. Microwaves were conventionally used for military communication, and of course short wave and long wave is radio communications, long wave is submarine communication, and so on. So it's not really important to mug up these numbers, but you should get a feel of these numbers to see which frequencies work for which applications. And this is a table put out by ITU, International Telecommunication Union. They say that these are the carrier frequencies that one should use so that there is compatibility between different cellular or different users. So they classify RF as anywhere between 3 to 3 gigahertz, 3 hertz to 3 gigahertz. In between you have all this UHF, VHF, MF, HF and so on, right. Again I am repeating, I mean this is not a mug up, but this is to kind of understand the order of magnitudes, okay. Microwave, again used for satellite and radar systems, they go from 30 hertz to anyway up to 3 terahertz actually. Now this range is very interesting, 3 to 30 gigahertz. Most of the radars operating today are in this range, most of the radars, right, whether it is atmospheric radars, weather radars, synthetic aperture radars, or for military communication, they operate either under SC, X, KU, K, Ka. These are the bands in radar ranges, right. So this is RF and microwave. So they typically end at kind of 300 gigahertz, and optical frequencies, again ITU standards start specifying in terms of different bands. Here we stopped writing frequencies and then we started writing wavelengths, right? Simply because the moment you go to optical frequencies, the frequencies become very large. The point of reference or the convention is to write in terms of wavelengths next, right? There is no specific reason. You could also write it in terms of frequencies, but it is just that probably the numbers are very large, you start writing in terms of wavelengths. Applications we will talk about later, but original band is O band, which is 1260 to 1360. Then you have the E band. The most conventional band, that is why it is called conventional, right? C band is 1530 to 1565 nanometer. So, correspondingly you can now calculate the carrier frequency. It will be somewhere close to 300. 500 was 500 nanometer was 600 terahertz. So, 1500 nanometer would be about 200 terahertz. So, roughly around 200 terahertz is the carrier frequency for optical communication. So, these are things, these are numbers which you should have at the back of your head when you say we are doing optical communication. Our carrier frequency is of the order of 200 terahertz, okay, which means allowed bandwidth is really large. People have started using long bands 1565 to 1625 and ultra long band, this is currently not used, but turns out that the capacity in optical fiber link is also exceeding. So, the current trend is actually to explore the other bands in optical communication, find out source, find out detectors for all these wavelengths, okay. And I said the choice of your carrier frequency is going to depend on your attenuation. One is bandwidth and the second is attenuation. So, let us look at how the attenuation is faring. If you are looking at atmospheric attenuation, it turns out that the total attenuation is this red line. So, y axis is specific attenuation, which means attenuation per kilometer. This is dB per kilometer and this is frequency. So, it is radio frequency 1 to 350 gigahertz, right. So, it is typical frequencies used in wireless and radar systems, okay. It is minimal, which is less than 0.01, I mean attenuation is up to 10 gigahertz, atmospheric loss is really low from 1 to about 8 or 9 gigahertz, which is why all your conventional cellular bands are in 3 gigahertz and 3.5 gigahertz and now you are moving to 6 gigahertz and so on, right. But there are certain frequencies for which, so this yellow line, this orange line is because of the absorption of water vapor. We will talk about absorption at a later stage. Essentially water vapor molecules have certain molecular resonances. So, if you go in and these molecular bonds have natural resonant frequencies. So, when you are exciting the system near its natural resonant frequency, you know that absorption will be higher, right. So, when you are exciting the system, the forcing frequency is close to the natural frequency of the system, you say there is resonance, and when there is resonance the absorption is larger. So, these bands are corresponding to, this orange band was corresponding to water vapor and then oxygen is this blue line, right. So, there are specific ranges you want to avoid when you are trying to use carrier frequencies because of, you can't have atmosphere without oxygen, you can't have atmosphere without water vapor. So, you want to avoid those ranges if you were to use these frequencies. But mostly the bandwidth here is limited due to carrier frequency. If I take 3.5 gigahertz cellular operating frequency, what is the largest bandwidth? According to the thumb rule I said, you can put 0.3, which is 300 megahertz. But what is typically used is 30 megahertz or 20 megahertz for seamless error free operation in cellular band. So, what if you want to carry larger bandwidth, you have to increase your carrier frequency, okay, and that is where you will start using copper cables. So, free space is not possible, you will start using copper cables. Now, this plot tells you for different types of copper cables what is the kind of attenuation. So, this is a coaxial, conventional coaxial line where you say the attenuation is about 100 to 1000 as you change your frequency of operation from 100 kilohertz to 100 megahertz. So, which means if you are trying to use a carrier frequency of 100 megahertz, within 1 kilometer of propagation, you have 1000 dB attenuation, orders of magnitude difference from what you transmitted to what you received. So, if you are going for higher frequencies, you have learned probably in your waveguide theory or your transmission line theory that you need to design specific capacitances and specific inductances so as to cater to higher frequencies, right. So, for very high frequencies you would use, these are WG16, WG10 are specific waveguide designs. These are rectangular waveguide designs of specific dimensions, specific material, specific dielectric inside the waveguide, which will work for specific frequencies. Optical fiber on the other hand, now when we talk about for optical fiber, now we are talking about bandwidth in optical fiber, right. So, this figure has to be interpreted very carefully. Here when you talk about optical fiber, you cannot obviously transport a 10 megahertz signal in an optical fiber, the dielectric will attenuate. But what we are now talking about is a bandwidth, right. So, as your bandwidth goes higher from 100 kilohertz to 10 gigahertz bandwidth, the attenuation is the same. What is the carrier frequency for optical fiber? It is not 100 kilohertz to 10 ki. The x axis now is representing bandwidth. The carrier frequency is still 1550 or the one of the bands that we have considered, right. But what we are trying to say is that irrespective of the bandwidth, the attenuation is the same for an optical fiber. So, copper cables, the bandwidth is limited because of the transmission line losses. Optical fiber, the bandwidth is not limited because of the transmission. There are other things which will limit the bandwidth of an optical fiber, which we will learn in the course, during the course. Optical fiber, you can put in a carrier frequency of 200 terahertz. It does not mean that we can very successfully transmit 200 gigahertz kind of data rates or bandwidths in an optical fiber. There are challenges even in that, but it is not posed by the channel. The challenge is not coming because the fiber attenuates higher frequencies. The challenge is coming because of something else. It comes from the transmitter, it comes from the receiver. So, when we learn about transmitters and receivers, we will understand specifically what is the largest bandwidth that can be provided by this transmitter versus another transmitter, right. So, the reason we are looking at bandwidth, attenuation, carrier frequency right now is also to say that when we learn further about transmitters and receivers, this is one question you have to keep asking. What is the largest frequency? What is the largest bandwidth? If I use a specific transmitter, for example, if I use an LED, if I use a laser, or what are the fundamental limits in terms of the largest frequency, largest bandwidth that I can transport? What we know is that as far as the fiber is concerned, the channel does not pose any limitation.